Archiving started.
Welcome to the recorded lecture for Module 3, and the goals of this recorded lecture are to provide a description of pressure losses that we may experience in a local exhaust ventilation system. So we've talked about pressure losses in terms of hoods, and as we move air through our ventilation system, through the hood, we experience some losses, and we just need to account for those losses in order to ensure that we, at the end of our ventilation system design, we are selecting a fan that will overcome those losses and be able to deliver the CFM that we have prescribed for our system. So today we're going to carry on that discussion of pressure losses, and my apologies in terms of I'm jumping around quite a bit in our textbook from Chapter 3 to Chapter 9, and then air cleaners are Chapter 8. I'm not going to talk about air cleaners in terms of the recorded lecture today, but it's an additional PowerPoint and reading material that I'd like you to be familiar with. But I'm jumping around because I'm trying to take baby steps in terms of our understanding of local exhaust ventilation systems and the design of them. And I felt that some material was introduced a little too early in Chapter 3, and so I'm covering it now. And then some of the material in Chapter 9 I feel is important to talk about now, and then we'll be putting that all together eventually in terms of design of our system. So bear with me. It gets better in terms of I won't be jumping around quite as much as I am with this module in the future. So this is a little redundant with what I just said. We need to account for losses in our system as we move through, and we calculate them in terms of a total pressure loss. So we've talked about hood entry loss already, and the Chapter 8 has some good information in terms of when we have an air cleaner, an air pollution control device in our system, which is typically very important. From an environmental standpoint, we don't want to capture contaminant within our work environment and just simply release it into the ambient environment. We typically need to have some type of air cleaner device associated with that. Also, if we were to capture heavy particulate load and we didn't have an air cleaner device prior to the fan, we would have some problems. It would quickly degrade our fan components as well as create a potential explosive mixture. So air pollution control devices are very important, but they typically are a major contributor to the overall pressure loss that we're experiencing with our local exhaust ventilation system. So I'd like you to read Chapter 8 for more information on those, as well as review the PowerPoints provided on air cleaning devices or air pollution control devices. But what we're going to focus on in this lecture are friction losses associated with moving air through sections of ductwork, and then also when we have various fittings, we put bends or elbows in our system, what are the losses associated with that? And so we already know that hood entry loss is a factor of F, a loss coefficient multiplied by velocity pressure. And so we now will take a similar approach with friction losses associated with moving air through our system. So friction losses represent the effect of drag forces as the fluid or the air moves over the duct surface. So it's a function of duct velocity, duct diameter, air density, air viscosity, as well as the surface roughness of our ductwork. So if we have a section of ductwork and it has substantial wear and the inside of the ductwork is quite rough in surface, and we're moving air through that system at a pretty high velocity, then we can expect a relatively high friction loss versus moving air through a smooth section of ductwork at a lower velocity. And so there's a couple of different ways that we can account for friction losses. The first one is presented in Formula 3.16 in the 28th edition of your textbook. Now, some of you have contacted me and said, hey, I got a 27th edition, or I have a 26th edition, or even as far back as 25th edition. Can I use it? And yeah, I have no problem with it. There haven't been substantial changes through the years, but the one thing you will run into is when I present a formula number, it may be a little different in your version of your textbook based on the edition that you have. So what I've referenced here is the latest and greatest edition, the 28th. So Formula 3.16 says, this is what we use to calculate a friction loss from drag through a straight section of ductwork, so in inches water gauge. So we have a 10-inch diameter duct, and it's 25 feet long, and we have a straight section of it, and we're moving air through it at 2,000 feet per minute. What type of friction loss might we expect with that section of ductwork? Well, we can easily calculate it with this formula. The busy part of this formula is our factor of F, or our loss factor associated with friction through the ductwork. And that becomes busy because we have to calculate F in order to plug it into the F multiplied by the length of the ductwork multiplied by velocity pressure gives us our loss through our ductwork. So one method that's presented in Chapter 3 is to use a formula for calculating F, and this formula has constants, lower case A, B, and C, that are based on Table 3.2. So if we jump to Table 3.2, we see that depending on what our ductwork is comprised of, what it's made out of, we have different constants that we use for A, B, and C. Now, the numbers that you see in the brackets next to the numbers in column A are System International units. I'd like you to use the numbers without the brackets, please. And so let's say we had a very common ductwork, which is galvanized metal. The galvanized metal would be under the sheet metal category, and so our constants for A are 0.0307, B 0.533, and C 0.612. So we go back and we have the constant A multiplied by velocity to the B power over Q to the C power. Q, of course, is in CFM. Velocity is in feet per minute. And so we'll use an example here. We have a 10-foot, 24-inch diameter galvanized ductwork. Air is flowing through at 4,000 feet per minute. What is the friction loss from drag through this section? Well, we know our friction loss formula, but we have to calculate F based on our constants that we get from Table 3.2. So since it's galvanized, we use the galvanized metal constants, and we have A, 0.0307, multiplied by our velocity to the B power, which is 0.533, divided by Q. How did we get Q here? Well, remember, Q equals VA. Our V is provided in feet per minute, and we find the area by taking the cross-sectional area associated with a 24-inch diameter ductwork. And when we do that, we get a Q of 12,566 CFM, and we bring that to the C power, and C units for galvanized metal are provided in the previous table. Multiply it by 10-foot lengths and our velocity pressure of 0.997 inches water gauge. How did we get that? Well, we have a velocity given to us in feet per minute, and we know that under STP conditions, a velocity divided by 4005 squared gives us our velocity pressure. And so we end up with a friction loss of 0.079 inches water gauge. And that doesn't mean a lot to us right now, but it will be important as we put all this together in our entire system. That's a loss that's a part of our component of our system, and something that we need to add up as we go. We're going to be adding up the losses that we're experiencing as air moves through our system. So we know how to calculate losses for a hood now, and we know how to calculate losses for straight sections of ductwork. But there's another method as well, and it doesn't matter what method you use, whatever one works best for you. And that other method is a table that's provided in, if you have the latest editions, it's Table 9.4. If you have an early edition, you'll probably find that at Table 5.5. And here's what the table looks like. We have the friction loss multiplied by velocity pressure per foot. So we're using the same formula, but instead of using a calculating F based on Table 3.2, we can find F by using this table. So for example, let's say that we had a 8-inch diameter duct and our velocity through our system was 3,000 feet per minute. Then we go across and we look under 3,000 feet per minute, and our F, our loss associated with moving air through our system at 8-inch diameter duct, 3,000 feet per minute, is 0.031. And then we can use that, multiply it by the length of the ductwork, multiplied by velocity pressure, and we have the loss associated with our straight section of ductwork. So if we use the same values that was used in the previous example where we used Table 3.2, we see that if we find the 24-inch diameter duct at 4,000 feet per minute, 24-inch diameter duct and 4,000 feet per minute puts us at a loss of about 0.008. And so we plug it into our relationship here with the loss factor multiplied by the length of the ductwork multiplied by velocity pressure. And we get a loss associated with that 10-foot section of ductwork of 0.0798. So that is pretty darn close to the 0.079 we found with the other method of calculation. And so you can see how both of these methods correlate pretty well in terms of finding the loss associated with moving air through straight sections of ductwork. Well, most of the time our ductwork will be round. Why round? Well, it resists collapsing better than other shapes. It provides better transport conditions. In other words, the velocity remains relatively uniform throughout that section of ductwork, and it resists settling of materials. But every once in a while, you'll run in perhaps into an older system in which your metal ductwork will be rectangular or square, and if that's the case, all of these tables that we're going to be using in terms of friction loss and so forth are based on round ducts. And so if you do have a square or rectangular duct that is within an existing system, you can find the friction loss for non-circular shapes by using a table as well. And these are circular equivalent tables. Okay. And in your textbook, it talks about very odd shapes like triangular. I have never seen a triangular ductwork in my lifetime, but they obviously exist based on our author's comments. And so there's a formula that one can use if you did have a round or rectangular duct, and that is to take your one side in inches, and that's A, multiplied by the other side in inches, and that's B to the 0.625 power divided by A plus B to the 0.25 power, and multiply that by 1.3. So that's one method. A much simpler, quicker method is in Table 9.5 if you have the later editions, or 5.9 if you have the older 25th edition. And so Using the calculation method, if we had a 12-inch by 12-inch square ductwork, we would get a round equivalent diameter of 3.1 or 13 inches. Excuse me. That would be the equivalent diameter if we had if that duct were round, 13 inches. Or you can use a table in your textbook, Table 9.5, and you get 13.1 inches. So you can use the calculation method or the table. We won't spend considerable time on that because most of the ductwork will be round, but in the event that you don't have a round one, how can you get the circular equivalent? Through that very simple formula or by using a table. One other thing that we will commonly experience with ventilation systems is the need to make our ductwork bigger or smaller through contraction or through expansions. We make it bigger through expansions, or we make it smaller through contraction. So this figure in your PowerPoint on this slide is an example of a contraction. We're going from a section of ductwork, and then we're going to a smaller section of ductwork, and so we have a contraction here in the middle of those two sections. Okay, so contractions are used when we need to reduce the fit, perhaps into a tight space. Maybe at the end of our system, past the fan, we want a high discharge velocity for some reason out of the stack. Maybe we have to fit onto an air cleaner opening, or maybe we have to fit our ductwork onto a fan opening. There can be many, many reasons, but contractions and expansions are pretty common within a local exhaust ventilation system. So there is an additional figure that's very important for expansions and contractions, and it's found in Chapter 9. It's figure 9D. And when I put it up on this PowerPoint, it's a little bit more difficult to see than having it in front of you in your textbook. What I do with my textbook is I get little sticky tabs, and I mark all of the important figures and tables that I'm discussing and mentioning in the recorded lectures or that I might have in the PowerPoint. I would mark those so that you could quickly go to them as you're working on assignments or working on an exam. I'm providing scans for most of these within the PowerPoints, but it's a lot easier if you have it all marked in your textbook and you know right where to go. But this busy slide presents a formula. If you look right here and right here, as well as right here and right here, you will see 4 different formulas. And let's talk about the bottom section first. So the bottom section are static pressure losses for contractions. And so there's 2 different types of contraction. One is a gradual one where we have an angle. That's the one on the left side. And the other one is an abrupt one where we abruptly go from a particular size to a smaller size. And notice with the angled one, we have the taper angle in degrees, and then we have an L or a loss factor associated with that taper angle. And then we have the static pressure going in. So number 1 section is going in, number 2 is coming out. So the static pressure coming in minus velocity pressure out, velocity pressure 2, minus velocity pressure 1, minus the loss factor multiplied by velocity pressure 2, multiplied by, or subtract, minus, velocity pressure 1. So that all we're doing with that formula is accounting for the change in static pressure by having a contraction in our system. So we went into, or we came up to the contraction with a particular static pressure loss, then air moves through our contraction, and we should have an even higher static pressure loss. And so is the contraction gradual with an angle, or is it abrupt? If it's abrupt, we take the area of 2 divided by the area of 1 to get our loss factor of K. And I wrote in here this, I scratched out 0.4 on this table and wrote in 0.5 because that's an error within your textbook. Expansions, on the other hand, we're going from a smaller diameter to a larger diameter, and so we're actually going to regain some of our static pressure we had coming into the expansion. So again, we have separate formulas. Will you have to memorize these formulas? Oh, of course not. You'll always be able to access your textbook, and this is an important one to put a tab on. And if you're taking the CIH, you'll see this particular figure within the formula sheets for the CIH exam. So it's a good one to know, but you certainly won't have to memorize this information. So expansions are used just like contractions to fit a particular piece of equipment, or maybe we want to slow air down. We want to decrease the velocity and therefore decrease velocity pressure. We can do that with an expansion. But we want to be careful. We don't want to slow air down too far because we can get a velocity that's below the minimum transport velocity. So that's a new term that I'm going to talk about at the end of this lecture, transport velocity. So we know what capture velocity, capturing a contaminant in front of the hood. Now we want to make sure that contaminant stays entrained in the air, so we have minimum transport velocities for various contaminants. And or we might have to fit onto a fan or an air cleaner. They're just like contractions. There can be many reasons for expansions. How do we know if we have an expansion or a contraction? Well, contractions go from larger to smaller. Expansions go from smaller to larger. And with expansions, we regain some static pressure loss. And with contractions, we lose static pressure loss, or have increased static pressure loss. And so here are the formulas that I just referred to in that figure, and I've just written them out here. So there's the formula for a contraction where we have an angle, and then we have abrupt contractions, and a slightly different formula for them, and expansions. And expansions are based on the diameter now of d2 over d1. So let's look at a couple of examples of how we can use this. So if we have air at volume flow rate of 4,500 SCFM, so S refers to under standard conditions. We're going to talk about non-standard conditions after exam 1. And it's traveling through a contraction. So we're going from an 18-inch diameter to a 14-inch diameter duct. It's a tapered angle contraction. The inlet static pressure is -2 inches water gauge. What's the outlet static pressure? What I do to help me with these scenarios is I like to draw a little picture. So just like we saw with this contraction here, we have a certain diameter ductwork, we have a tapered angle contraction, and then we have a next section of ductwork. I would do the same thing with these exercises, just so in your mind you can see, it'll make sense to you what you have. So we're going from 18 to 14 inches, and we have a taper angle of 30 degrees. That'll be important to look at what the L loss factor is for a 30-degree angle. Going in, we had -2 inches water gauge static pressure. The velocity pressure in section 2, how can we find that? Well, we have Q, and we have the cross-sectional area, or we have the diameter, so we can find the cross-sectional area and find velocity. If we have velocity, then we can find velocity pressure. The velocity pressure that you get should be 1.1 inches water gauge. Velocity pressure in section 1 is not minus. Velocity pressure is never minus. Velocity pressure in section 1 is 0.4 inches water gauge. How did we get that? Well, we have Q, we have an 18-inch diameter duct, so we can find A. If we have Q and A, we can find V. If we have V, we can find velocity pressure. So we should get a velocity pressure of 0.4 inches water gauge for BP1. If you're not getting these values when you go through my PowerPoint, please contact me if you need additional help, or if that isn't making sense, please let me know. And we do our math. We get a static pressure of minus 2.79 after air moves through that contraction. And it's a good idea to back up and say, does that make sense? We went in with minus 2 inches water gauge. We come out with additional static pressure loss, which we would expect because we have a contraction. And if we have an expansion, here we have in this exercise, we're going in with minus 2 inches water gauge. In our answer, we have a lower static pressure loss, and that is what we will get with an expansion. We will regain some of the pressure loss that we had going into our system. So we talked so far about air moving through straight sections of ductwork, as well as air moving through a contraction or an expansion. Let's talk about now when we put a bend or an elbow or a branch entry into our system. And so there's a couple of key figures that I'd like you to put a sticky tab on in your book. And that first one is figure 9E. And notice on figure 9E that we are provided a variety of different elbows. So an elbow is nothing more than a bend within your ductwork. So we have stamps, which is a smooth one. It doesn't have pieces all fitted together. It's one piece that is typically factory molded to have that particular bend. Or we have a 5-piece or a 4-piece or a 3-piece. A mitered is something that we typically want to avoid in a local exhaust ventilation system because it's very difficult for air to, well, not for air, but the particulate matter entrained in air to stay entrained and make that 90-degree turn. And so mitered we typically want to avoid, but we still see that pictured here in our system. So here we have, based on what type of elbow we have a loss factor, and that loss factor is based on the radius of curvature, which I will provide to you, divided by the diameter of your ductwork in inches. And so if we look at this in terms of an exercise, we have a 12-inch diameter duct, and the radius of curvature is 18 inches. And so we have 12-inch, or 18 over 12 is 1.5, and that happened to be a 4-piece elbow. So radius over diameter 1.5, and we have a 4-piece elbow, and we get a loss factor of 0.27 from the chart, a K value of 0.27. And we would multiply that by velocity pressure to get the total loss experienced by having that elbow in our system. We also can experience losses by having branch entries into our system. So here at the top we see a section of ductwork, and then we have a branch entry coming in at the bottom of that ductwork. And based on the angle of our branch entry, we have a loss associated with doing that. So notice if we were to have a 90-degree branch entry, we have a tremendous loss associated with it compared to the others. And that makes sense. If we had two airstreams coming in perpendicular to one another, we would expect a lot of turbulence, and that wouldn't be a real efficient design. So we usually design them between 10 and 35 degrees in terms, if we can, in terms of our entry into our main system. And based on that angle, we find a loss, and we multiply that loss by velocity pressure. And so, again, this is figure 9F, another one that you want to tab. And if you have an older edition, you might, way old, 25th edition, you might find it in figure 517. So we assume this loss to occur in the branch, and so how could we use this? Well, let's say we have a 45-degree branch entry. 45-degree branch entry, loss factor of 0.28. So 0.28 multiplied by velocity pressure is the loss associated with having that entry come into our system. Another one, what is the actual loss in inches water gauge for a branch entry of 30 degrees where the entry velocity is 4,500 feet per minute? So we find, based on a 45-degree angle, or 30-degree angle, excuse me, we find a loss factor of 0.18, and then 4,500 feet per minute gives us a velocity pressure of 1.26. So the actual static pressure loss associated with air moving through our system when we have this branch entry is 0.23 inches water gauge. So throwing out a lot at you, I know, but it'll all make sense when we put this together and we start to actually design a ventilation system based on all these rules. One last thing I'd like to mention, and we'll be talking about this in more detail as we move along, but we looked at capture velocities already in Module 2, and I said how capture velocities are very important because there are minimum capture velocities we want to achieve in order to ensure that we could capture our contaminant. And now this is another table that is important to us, and we'll be talking much more detail in Chapter 5 and Chapter 9 about this. But this is the minimum duct design velocities, or these are the minimum duct design velocities. So what does this mean? If we capture welding fumes, in order to keep the welding fumes entrained in our airstream, we want to have our system operating at a velocity, duct velocity of 2,000 to 2,500 feet per minute. If we're not achieving that, then those fumes will, let's say it's too low. Let's say our velocity is only 1,000 feet per minute. We run the risk of those particles, those very small particles or fumes, dropping out of our airstream and not reaching our air cleaner. And let's say we had a heavy particulate and we didn't have adequate duct design velocity or duct transport velocity. Eventually that heavy particulate would drop out of the airstream and would begin to build up in our system, and we would have our fan operating, but nothing is moving through our system because we have a major plug in the system due to particulate buildup. And so this duct transport velocity, minimum duct design transport velocities are very important to us. And notice, the heavier the particulate, the higher the transport velocity, just like capture velocity was. Whereas if we have gases, vapors, 1,000 to 2,000 feet per minute is typically adequate for those in order to keep them entrained through our system. Well, that concludes our recorded lecture for this Module 3. Again, don't hesitate to ask if you are having questions or problems as you're going through these. And I guess that's it. Nothing more. Have a good one.